Hey everybody, in this video we're going to take a look at how you explain some properties like melting point, boiling point, etc. for ionic and metallic substances specifically. Here we're going to compare calcium oxide to potassium fluoride to try to make a guess or a prediction about which would have the lower melting point. You can see a list of 6 different factors over here that you've got to consider when making this analysis, and you can apply these same 6 things to really any scenario you're given when it comes to ionic or metallic substances. The first thing we've got to know is exactly what type of bonds are holding these substances together. Is it ionic or is it metallic? Here with calcium oxide, I know that calcium is a metal because it's on the left-hand side of the periodic table, whereas oxygen is a non-metal. And anytime a metal is bonded to a non-metal, that bond is going to be an ionic bond. And you've got the same exact setup with potassium fluoride. Now that I know there are ionic bonds present holding these substances together, or these particles together, I've got to start to analyze how strong they are, or in some cases how weak they are. And to do that, there's 3 factors. I'm going to list them as 1, 2, and 3 down here, so you can sort of know what's what when it comes to this list. The first one is, what are the charges of the ions involved? What are the radii of those ions? In other words, are they big or are they small? And then the last thing is, how many delocalized electrons are there in each substance in a relative sense? Notice, however, this is for metallic substances only. So because both of these are ionic, I can ignore that third one, and we're only going to be focusing on the first 2. So let's go back to number 1 to begin, and we'll compare the charges of the ions in each substance. Calcium in the alkaline earth metal column has a +2 charge. Oxygen's column tends to get a -2 charge, so I've got a +2 and a -2 in calcium oxide. Potassium forms a +1 charge. It's in the first column of the periodic table, the alkali metals, and they all form a +1. Fluorine is a halogen, and when it becomes an ion, halogens tend to form -1 ions. So in KF, we've got a +1, -1. Notice it's a pretty clear difference. Potassium oxide has higher charges, or what we would describe as higher charge magnitudes, because 2 is bigger than 1. Next, let's take a look at the ionic radii and how they might compare to each other. To do that, I'm going to pull in a periodic table, and we'll look at some of the patterns that exist here in terms of radius. Now, the first thing I notice is that potassium and calcium are both right next to each other in row 4, whereas oxygen and fluorine are right next to each other in row 2. Being farther down on the periodic table, like potassium and calcium are in row 4, mean that they are both going to be quite a bit larger than oxygen and fluorine. In comparison to each other, I can see that potassium is a little bit further to the left, and that means potassium is going to be a little bit larger than calcium. So I'm just going to try to make some notes about those patterns here. So maybe first I'll write that calcium is smaller in comparison to potassium, so those 2 are kind of related to each other. At the same time, bring back my periodic table here. Oxygen compared to fluorine, oxygen is actually further to the left. So oxygen, if that pattern holds, because it usually does, oxygen is going to be a little bit larger than fluorine, so we'll make a note of that. So oxygen is larger, fluorine is going to be smaller, and we'll connect those 2 because they're compared to each other. The one thing we're not denoting here is remembering that calcium and potassium are both larger than oxygen and fluorine combined. So the one thing to note here is that the patterns in ionic radii for these 2 substances are not as clear, right? Calcium oxide has a smaller one with a larger one, same thing with potassium fluoride, so that's not as clear cut what those differences are going to be. Okay, so all of that work and those comparisons were so we could answer this question right here: bond strength comparison, and why. In other words, both of these compounds are held together with ionic bonds. Which of those ionic bonds is stronger? We can tell that by looking at these 2 factors. I want to clarify, though, exactly how you do that and what these things are supposed to tell you. Number 1 on the list, if you've got stronger bonds, that's going to be associated with larger charge magnitudes, or I'll just kind of simply state larger charges within the ions of the substance, and that's what we've got with calcium oxide with those 2s. Stronger bonds are also going to be associated with smaller ions. That allows the ions, or at least the ion centers, to be closer together. And when charged particles can be closer together, they're going to be more strongly attracted as well. And I'm going to add one little asterisk next to number 1, because a larger charge magnitude often plays a larger role than the sizes of the ions. And that's going to be key here, because remember, my comparisons in ionic radii were kind of all over the place, right? Some are smaller, some are larger. There's no clear-cut difference between these two compounds. However, that ends up not mattering at all, because I have a very clear difference in the more important factor. That's kind of the purpose of this asterisk. If you've got a larger difference in charge magnitude, in most scenarios you can pay attention to that and then essentially ignore any differences in ionic radii. Essentially what this means is that the charges of 2 in calcium oxide are going to result in stronger ionic bonds in calcium oxide, whereas potassium fluoride is going to have weaker ionic bonds. All of this is so we can predict the property of these substances, which is, again, which would have the lower melting point. Anytime there are stronger bonds between the particles within a substance, that's going to correlate to certain types of properties. In terms of melting point, that's going to result in a higher melting point. That means the weaker ionic bonds in potassium fluoride are going to result in a lower melting point. Now I've got my answer. Which substance would have the lower melting point? It's going to be potassium fluoride, because its ionic bonds are weaker. That also wraps it up for this video. Thanks a lot for watching.